Now we're going to talk about the voltage divider, where we're going to use it in simplifying every circuit that is presented to you for the midterm exam and the final exam. For a very quick reminder of a couple of things here, let's have a look at the conventional current direction and the electron flow direction. So conventional current direction is this, and it happens so that a long time ago, when we didn't know matter was built up of electrons, protons, and neutrons in the atoms and the molecules. People just arbitrarily said, we are going to make this the direction of the flow of the current. And then a couple of hundred years later, people realized that, oh, okay, so the electrons are the carriers of the charge in electrical current. They actually physically move to create the electrical current, and they being negatively charged, leaving the negative part of the power supply in the DC at least. Now we have a couple of directions. You can do the electron flow direction, or you can do the conventional current direction. You're going to find out that I will always use the conventional current flow direction. That's because throughout my education and training, that's the only direction I was encountering in textbooks. All right, so that's the first thing. The second thing is this. We have something that is called Kirchhoff's voltage law. Kirchhoff's voltage law says that if you take a circuit like this and you add up all the voltages, they have to equal to zero. In other words, you'll have to have the electromotive force in the current in the circuit equal to all the voltage drops in that voltage in that circuit. So that would be your Kirchhoff's voltage law. In this case, we are representing a few things. Let's have a look at the few things we are representing. So number one, we have R1, and the voltage drop across it is V1. R2, the voltage drop across it is V2, and R3 has the V3. And as you can see, there are your kind of polarities, because in DC there is always the idea of polarity. So the positive here is going to go and meet the positive at the first resistance. Basically, the node analysis actually applies here as well. So if I take my kind of node like this, if this is my node, if everything here is the same voltage or the potential, electrical potential, it only makes sense that the positive on this side is going to be also the positive on this side. That's the principle you can remember. However, obviously, while the electrons are flowing through, they are going to lose, as we said, energy, and therefore a voltage drop is happening. And as a result, we have a negative here, just to show that this pole compared to that pole is of less potential. So the negative is a lower electrical potential compared to the positive, which is a higher potential. The same thing happens when the electrons are going through every single component in the diagram. When they enter with a positive or more potential, and they leave with less potential because they are losing energy as they go through each resistor. The idea is that you better lose all the energy before you get back to the power supply. That's the whole idea. So if you don't consume all the voltage that is generated in that circuit, and you try to bring some of the voltage or the energy back to the power supply might not like that very much. So in any circuit, this rule, Kirchhoff's voltage law, is going to apply. Now, when we do current divider or voltage divider, please remember that we're going to do them only as they apply to two resistors. Never three. That's not in the scope of this course. It's only two resistors. So this is an example that we can talk about right now. In this example, what you're seeing is that there is the power supply. There's the first resistor and there's the second resistor. Obviously, Kirchhoff's law is going to say that the 10 volts, that is a very wide, the 10 volts that are generated as EMF, the electromotive force, are supposed to be equal to V1, which is the same as VAB, and plus V2, which is VBC. So this is your Kirchhoff's, or the application of Kirchhoff's voltage law. Now, VAB is, okay, so let's say VAB is the voltage from A to B, which is the opposite of the voltage from B to A. So VAB would be equal to negative VBA. That direction, remember DC is a single direction, so it's a direct current. It flows in one direction only. Therefore, there is a direction in DC. In AC, the current flows in both directions, and therefore polarity is not, the concept of polarity in AC is a completely different thing than AC. In AC, it represents direction. All right, now, how are we using this? I'm going to call it a technique because it is a simplification of rules. So the technique goes like this. V1, which is a division, right? Voltage divider, it's a division, is going to be equal to a certain dividing ratio multiplied by the voltage supply. Voltage supply is going to be the voltage that is across the two resistors we're working on. Remember, voltage divider and current divider, we are going to apply them on two resistors only. So there will be voltage applied on two resistors, and we are going to call that Vs. Then we're going to calculate the voltage that is now given to one of those two resistors. In this case, V1 is going to be equal to R1 over R1 plus R2. And this rule is not going to change. You're going to apply this rule over and over again. In the same kind of cookie cutter formula, you can say V2 equals to R2 over R1 plus R2 multiplied by Vs. And as you can see, there is a congruence between, if I know you can see this here, one here and one here, also two here and two here. So that's going to be the calculation of the voltage divider between, so basically taking a supply voltage across two resistors and then dividing it to two different voltages, V1 and V2. Now, sometimes you are going to be reminded of the fact that every EMF source, electromotive source, is going to be comprising of two elements: the source itself, the ideal source itself, and then its internal resistance. And of course, the internal resistance is going to be something that is in series with the voltage supply. And if you have a current supply, it will be in parallel with the current supply. But we're not discussing current supplies, only voltage supplies here. Now, I want you to have a look, a close look at this thing here, and just ignore this voltmeter for a second here. I'm just deleting this voltmeter in its entirety. What you're going to see is that there is a simple resistor 1, resistor 2 series circuit connected to the power supply. In this case, what you're going to say is, okay, the voltage of the load is going to be what? It's going to be the fraction, the ratio, dividing ratio, multiplied by the Vs, right? Vs is the voltage that is applied on both resistors. So the voltage between this point here and this point here, this 2 points, the voltage is 65 volts. Okay, and then this is going to be RL over RL plus R internal. And that's how you calculate it. This is a ridiculous example because you're probably not going to have your load resistor so close in value to the internal resistor. That would be a very bad application of the principle. Anyway, so VL is going to be RL 3.3 ohms divided by 3.3 plus 0.5 multiplied by Vs is going to be 65. And if you do the calculation, you get your voltage, the voltage that is on the load.